Sometimes you just want to draw lots and lots of something without necessarily needing to control every single element. Take grass, for example. Who cares exactly where each strand of grass is? What matters is that there are enough of them to collectively look like grass, rather than individual strands. The same goes for particle effects like smoke, fire, and trail effects. Having enough of them is what matters the most. GameMaker has functions for drawing 2D particles and is efficient at drawing 2D sprites, but it has no built-in system for drawing lots of sprites in 3D. So let's make our own system instead. There are 3 components that will have to work together to make this work: a vertex format, a vertex buffer, and a shader. Let's start by defining a vertex format, shall we? Here you can define whatever info you want to store in each vertex. A vertex format will of course need a 3D position, right? Right? Right, well, get back to that. Let's only have a position in there for now. Let's make a vertex buffer and give it the new format, and to make a single strand of grass, we'll just make a single triangle by defining the 3 points of the triangle. In the draw event, I can set the shader to the grass shader and submit the vertex buffer with vertex submit. In order to actually make it appear on screen though, we also need to make the shader correspond to the vertex format we made. That is, have it take a 3D position as its only attribute. Also, since this is grass, it obviously has to be green. Okay, and we already have a blade of grass, albeit a very boring blade of grass, but it's a start. But, of course, a lawn consists of more than just a single blade of grass. Let's make it a bit more lush by adding multiple strands in a loop and scatter them randomly around the object's coordinates. And here we have a freshly grown lawn, but what happens if we place this in a 3D environment? So I copied the object over into the 3D gravity platformer, and a problem is immediately evident. The grass is paper thin and it's lying perfectly flat on the ground. What I want to do now is to make the grass point in the direction it's growing, while also facing the camera. This is called cylindrical billboarding. Right, so right now we're defining each vertex of the triangle. We're gonna have to make some changes in order to give the shader more power to control the vertices. If, instead of baking the coordinates of the vertices into the vertex buffer, we only store the position of the base of the grass strand, as well as the direction it's pointing, we can reconstruct the actual coordinates of the vertices directly in the shader. We'll also need some way of identifying which vertex is which. I'll give it the pointing direction as a normal attribute, and as a temporary solution I'll identify the vertices by color. And like I mentioned, I'm going to give the strand the coordinates of the base of the blade. This unfortunately means that I have to duplicate the info and send the same coordinate to all 3 vertices. As for the identifying vertices by color part, I'm going to make one vertex perfectly red, one blue, and one green. In the shader, we have to modify the attributes to match the changes to the vertex format. We also need to supply the shader with some info about the width and height of the grass, and this can be done by sending the value to the shader as a uniform. Now let's go back to the drawing board for a second. Finding the position of the vertex labeled number 3 at the tip of the grass is easy enough. That's just the coordinates xyz plus the normal vector multiplied by the length of the grass. But how do we find the vertices labeled 1 and 2 though, if we only have the position of the base and the normal vector in 3D space? From the diagram, it seems like we're going to need a vector that is perpendicular to the normal vector, pointing in this direction. Oh, and the vector also has to be perpendicular to the looking direction of the camera. This is starting to sound like a job for the cross product. If you're not familiar, the cross product is a vector operation that takes in 2 vectors and returns a new vector that is perpendicular to both of the original vectors. So if we give it the normal vector of the grass and the vector from the camera's position to the base of the grass, we should get the vector we need. We could send the camera's position as a uniform as well, but GameMaker is already sending all the info we need to work it out directly in the shader. The view matrix contains the inverse of the world space orientation of the camera. If we work backwards and multiply the 3rd row of the view matrix by the whole matrix, we end up with the actual coordinates of the camera. Then we can use the cross product to make a vector pointing sideways. Now we gotta figure out which vertex we're currently processing so that we can displace it in the right direction. We're using colors as a temporary solution, and only one channel is active for each vertex. The red and green vertices should be displaced sideways, while the blue vertex should be displaced along the normal vector. And there we go, all the individual strands of grass are facing the camera while also pointing along their normal vector. Right, in order to control where and how many strands of grass are being drawn at the same time, I will control them with cluster objects. Each cluster object will be responsible for its own little cluster of grass, and I will only draw if it's within a reasonable distance to the player. At the moment, the grass is floating above the ground. This can be fixed by having the cluster object cast rays around itself from above the level, and placing the grass wherever the ray hits. Casting rays is easy enough when using Colmesh. For simplicity, I'm casting straight down along the z-axis for now, and I'd like to only cast the rays against solid objects. I'll also increase the size of the cluster and increase the number of strands it creates. Also, I'll move the cluster object to a more interesting part of the level geometry. I also gave them a slightly more pleasing to look at gradient texture. The grass seems to be following the ground nicely, just as planned. Let's talk some numbers though. Our vertex format currently contains a 3D position, a 3D normal, and a 4D color. In total, this is 28 bytes of data per vertex. If we spawn 500 triangles, and each triangle has 3 vertices, this adds up to 42 kilobytes for just this one cluster. I intend to fill my levels to the brim with grass, so this will quickly add up. But how much of this can we possibly get rid of? Well, I'd say we can remove practically all of it. Let me explain. Right now, every cluster object needs to create its own vertex buffer. This is because the vertex buffer contains info that is unique to the cluster object that created it. This part right here, the raycasting, places the grass in 3D space, so it's not like we can use the same vertex buffer anywhere else than precisely where it was created. Except, let's do exactly that. To do this, we'll have to accept some compromises. One is that we can't have a unique normal for each strand, so we can just remove that attribute from the vertex format and send a shared normal to the shader as a uniform instead. Another compromise slash optimization is to create a grid of say 5x5 points around the cluster object, and then cast a ray from each grid point. Then the grass can sample this grid when finding their position. Sure, we'll lose some precision, and the grass will kind of be draped over the level geometry instead of hugging it perfectly, but through mindful and clever placement of the cluster objects, I'd say this won't be a problem at all. Here's a simple code block for casting rays in a grid like I described. This is casting 5x5 rays and stores the z-value of the intersection in a linear array. I could use a 2D array for this, but trust me, a 1D array will be more useful later. I also visualized the grid by building a vertex buffer from it, so here you can see how it drapes over and intersects the terrain. Again, not a perfect solution, but it'll work okay. So how are we going to use this grid exactly? Well, we could sample from it when we're adding grass to the vertex buffer, but this kind of defeats the purpose of doing it this way. What I'm actually going to do is to send the grid to the shader as a uniform. Then the vertex only really needs to store the 2D coordinates where we want to sample the grid. I'll make these span from 0 to 1, and then I can completely remove the z-axis. In the shader, our grass starts out somewhere inside the unit square, since that's what we gave the vertex buffer. If we multiply the coordinates by the grid size, which at the moment is set to 5, we end up with a coordinate in a 5x5 grid. Now we can identify the 4 nearest grid points. To figure out the height at the coordinates of the grass, we can interpolate between the right and left values first, and then interpolate again between the 2 values we got. And here's what that would look like as a function in a shader. Now, there is one kind of advanced part that I don't want to postpone implementing any longer. All the rays are currently being cast along the z-axis. My game famously allows you to walk around on spherical planets, so this is a big limitation. I want to be able to place grass on any side of my planets, not just on the North Pole. To do this, I will somehow have to store the orientation of the cluster in 3D space. I've opted to using a matrix for this. For now, I'll build the matrix with no rotation and no scaling, but I'll put the coordinates of the cluster in here. This is why I also have to remove the coordinates from _x and _y, since they're added when transforming the 2D grid with the matrix transform vertex. Figuring out where the ray should be cast from and to requires some vector math, and since this is GameMaker, I'm doing it one dimension at a time. The matrix indices 8, 9 and 10 contain the up vector of the matrix, so I can use this directly in the ray casting. Once the raycasting is done and we get the 3D coordinates of the intersection, I'd like to store how far the intersection is along the cluster's up vector. This is a task for the dot product. I need to send the cluster matrix to the shader somehow. Here I can make use of the world matrix, which GameMaker always passes to the shader anyway. As I mentioned, the matrix contains the up vector of the cluster, so I can also remove this uniform. I still need to pass the size of the cluster though, so that I can reconstruct the world space coordinates of the grass strand in the shader. So now we're in shader, and I'm going to do this part live. We're currently getting the position directly from the attribute, but this is now a 2D position that goes between 0 and 1, and I want this to go between size and minus size. Let's just add that here, size. And we can remove the normal. So to make this go from size to minus size, we can multiply this by 2 and subtract 1. So now it goes from -1 to 1. And then we can multiply size by that. This is a 2D coordinate, so we have to use the x and y values. But this is a 3D coordinate, so we have a problem. Actually, I'm going to make this 4D just to make it even more difficult. So now we have to create a 4-dimensional vector from a 2-dimensional vector. Luckily, I made this function here earlier. This reads from the grid that I'm sending to the shader as a uniform. So we can place that in there, and we can use the inPosition.xy directly as the argument there. And for the last dimension, I'm just going to use 1. Now I'm going to use the world matrix to transform this coordinate here. I'll just copy this. And I'll put it into a separate variable, m. I'll name this the world, that's world, there we go. And I'll do m times that. This is actually the final world position of the strand. I removed the normal, so I have to make that again, and this is a vec3, I'll just name it n. And I can take that straight from the world matrix, like this, and I have to replace that in all the instances where this shows up. Now we have another problem. This position is in world space, but we're also using the world matrix down here. So I have to remove this from here, but okay, this is not a constant, so I actually have to multiply the two matrices manually. Position, this is already a 4-dimensional vector, and there we go. This should actually work. Nope, that did not work at all. Right, so position is a 4-dimensional vector, so we have to use x, y, z here, and here, and here, and here, and then we'll try again. And the grass actually does exactly what it's supposed to. It's no longer following the ground perfectly. So you can see some of them are kind of floating in the air. This is a sacrifice I don't mind making. Because look at this. The vertex buffer no longer contains any info that binds it to this cluster. That actually means that this vertex buffer is now infinitely reusable. All we have to do to add a new cluster to the game is to create a new grid, and then we can just submit the same vertex buffer for every single cluster. There are some more optimizations we can make. The vertex index is stored as a color. This is kind of wasteful, so we could just remove the color attribute, right? Wrong. Let's remove the position attribute and then figure out a way to encode the position into the color. For this we have a handy function called makeColorRGB. This takes in a value between 0 and 255 for each dimension, so I can simply just change the range for x and y accordingly. Then I can put the vertex index in the blue channel. So I'll identify them by 0, 1 or 2. The color is automatically normalized to a 0 to 1 range, so I can simply replace in position with in color in the position calculations. And I'll also modify the index checking to make sure we're processing the right vertex of the triangle. So by switching to using a color, we kind of reduced the resolution of the possible placements of grass to 255 by 255, and that is something I don't like. Also, the grass looks kind of boring. They're all the same size, the same width, the same length, the exact same color. I kind of want some variation between them. And we can solve both of those problems at the same time by adding a simple function to the shader. And that is a noise function. This should theoretically give us a unique value for each strand. So we can set the Y value here to a value that is unique to this strand. We actually we have a dimension that is unused in color, and that is W. Let's see here. Currently they're all set to 1. If we set them to, for example, the grass index equals 0, and then we can increase this and then put that there, and let's divide by strand num so that we get a value between 0 and 1. There we go. Now we can actually use the noise function directly to get some random values. Width times, let's say 0.8, and then vary it by 0.4 times noise. Okay, let's increase that to 1.4 just to exaggerate the noise effect. So I can see all the strands are different dimensions. Now, as I mentioned, the resolution of the position is kind of low. It's 255 by 255, but we can increase the effective resolution by adding some noise. So let's remove this and add a new vec2 called local position. Let's place that inside there. So let's add some noise to that, plus noise divided by 255. That should do the trick. Also, I don't want this to exceed 1, so let's do the minimum of that and 1. And there we go. Infinite resolution, baby.
I think it's time to add some more vertices to the grass. Triangles just don't do it for me anymore. Adding just one extra segment though actually requires adding 2 more triangles. I played around with the idea of adding just one triangle and then cutting away half of it, but this required discarding pixels in the fragment shader, so I discarded that idea. So we're adding segments 2 triangles at a time. The maximum value we can use for the vertex index is 255, so if we make it so that even values shift the vertex to the left and odd values to the right, we can actually segment the grass 127 times. Also, I can't let pass this opportunity to make the grass follow a curve. In the shader, I added a function for controlling the curve. The actual equation is just something I threw together that I thought looked okay, so it is subject to change, but my goal when making it was to allow for a curve that can have a variable horizontal displacement that also affects the shape of the curve. As in, the more the curve is displaced, the more the grass curves. Let me show you a 2D representation of what the curve looks like. I've mapped the horizontal displacement to the mouse position, so as I move the mouse, you can see how the curve bends. So what can we use this for? Well, having the grass wave in the wind is an obvious one. We can also make it avoid the player as if it's being stepped on, making the world feel a lot more dynamic. I also made a function for controlling the width of the grass as a function of where the segment is along the length of the grass. This lets us get rid of the triangular shape. The wind function is also just thrown together with sines and cosines, with the position of the grass and a time argument as input.
So, putting it all together, the grass now looks like this. It's gently waving in the wind. It's curving away from the center of the cluster. If I walk into the cluster, the grass is curving away. Look at this grass. You can't tell me this grass does not look good.
There are endless ways to optimize this further. Let's go through some of the changes I've made. Where I previously displaced the vertices sideways in world space, I am now doing it in projection space. This saves us from having to find the camera position, and it also gets rid of several matrix multiplications. When rendering the grass, you can use vertex submit ext to control how many strands are drawn, depending on how far away the player is, by changing the number of vertices that are submitted. Here I exaggerated the effect just to demonstrate. I could even completely get rid of the 2D position as well, and instead only store a more precise vertex index, which I can then use in the shader to generate the whole position with the noise function. Here's an attempt I made at making the number of segments vary depending on distance. It failed spectacularly, but after some more testing I managed to kinda get it working. Except it doesn't look very realistic with all the grass changing number of segments at the same time. With a little more tweaking though, I got it working exactly the way I wanted. Actually, I managed to pretty much completely hide the switching of the number of segments. Did you see it? Look again. Okay, let's have a closer look at one of the strands. Notice how the vertices kind of smoothly come out of the ground as I'm getting closer to the cluster. To me it makes more sense to place the grass inside a circle instead of a square. Getting a uniformly distributed random coordinate inside a circle can be done by getting a random angle and the square root of a random value for the distance, and then use trig to find the final coordinate. I like avoiding square roots and trig in my shaders when I can, so I will use a two-stage rejection sampling instead. This means that I first get a random point, then check if it's within the circle, and if it isn't, I find a new random point. In theory, you should repeat this process until it succeeds, but I'm happy with doing this just one time. Shaders also don't like if and else, so here's a shader-friendly way to code a two-stage rejection sampling. I made the cluster objects check for collisions with the gravity objects so that they orient themselves properly. This means I can place them around the planets in the level. I do intend to make a proper level editor at some point so that making levels will be more intuitive, but we'll have to take things one step at a time. In-game, I've made a grass manager object that is responsible for drawing the grass. It subdivides all the grass clusters into an octree structure. It also keeps track of the player's trail and only updates distances and checks the octree for nearby clusters when the player is far enough away from the previous trail point. Here's a slightly different variation to the width and height of the grass. And that's it for this week's video. This was a long one, and while I know there's a lot to keep track of, I hope the video's main message made it through. That the shader has a lot of control over vertices, and that you can and should shift some responsibility over from the vertex buffer to the shader. I originally planned to make this video about both grass and particles, but I think it's better to end it here and perhaps make a separate video about particles at another time. If you're still here, thank you so much for listening to me ramble about particles and vertices and vectors and other nonsense. I hope you look forward to the next installment, and in the meantime, feel free to comment and make suggestions in the comment section below. I'll see you around.